Our next speaker is Heping Wang from Capital Normal University in Beijing, and he will talk about Monte Carlo methods for LQ approximation.
First, I would like to thank organize of this workshop to give me a chance to give a talk here. My talk, the name of my talk is Monte Carlo methods for LQ approximation on periodic subnet space with mixed smoothness. In recent years, there has been increasing interest in Monte Carlo methods compared with deterministic methods. Monte Carlo methods have much sovereignty for computation of integral and for some function approximation problems due to their can speed up order of convergence. Monte Carlo methods can also be used to improve tractability in infinity information-based complexity theory, especially for problems of integration and approximation in uniform approximation. In this talk, we consider approximation of compact embedding of periodic subnet space of dominated mixed smoothness into LQ space by linear Monte Carlo methods that use arbitrary linear information. We construct linear Monte Carlo methods and obtain explicit-in-dimension estimates. These estimates come up with the rate of convergence. First, we give the definition of deterministic space and Monte Carlo methods. Let S f maps to G be a bounded linear operator between two Banach spaces, the so-called solution mapper. In this talk, we consider methods or methods that use continuous linear functions on F. We aim to approximate S for a put set by deterministic approximation methods of form in this case, where the mapper in this form where the mapper in A, called the information operator, stands for the process of gain information about from F belong to F, and the mapping from Rn to G represents the computation process and generate output in this form as approximation to SF. Using the input set is choose to uniball of BF. The information ANF is called non-adaptive if ANF is this, where LK belong to the dual space of F, and information ANF is called adaptive if the choice of functions may depend on previous obtained information. If the information ANF is non-adaptive and mapping phi is linear, then we call the deterministic method N is linear. Otherwise, we call ANF non-linear. By AN deterministic linear, we determine the class of all deterministic linear methods with the cardinality less than N. The broader class of nonlinear methods with class less than N is denoted by this. The worst case of deterministic methods at N is defined by this formula. Now we introduce the randomized methods, maybe also called the Monte Carlo algorithms, are understood as a measure mappers A in omega. This is from omega times f to g, where p this set denote Borel sigma algebra of f and g respectively. Omega sigma p is a suitable probability space for any fixed omega belong to omega. A in omega is a deterministic method with the cardinality A in omega. The number A f omega may be randomized and adaptive depend on the input, and the cardinality of A in omega is defined by this. If for each fixed omega belong to this set, then A omega is a deterministic linear mode method. Then we call A omega a randomized linear method, denoted by A in run linear, the method with cardinality less than n. Also, the nonlinear methods denoted by this. We remark that a measure deterministic method may be viewed as a randomized method that is independent of from omega belong to this. Hence, A in dimension can be regarded as subclass of A in run. The worst case of randomized method, A in omega, is defined by this. And this is also given in the previous talk. we define a minimum error of problem S as error of optimal algorithms is defined by this, where the diamond is belong to deterministic on run, and the star belong to linear or nonlinear. Usually we call run the Monte Carlo error or randomized case error, and it determines the worst case error of problem. We have the following inequalities. Now we introduce the space of smoothness. For D belong to the natural numbers, we have xp, and this T denotes torus. TD is normalized. We equip TD with normalized the big measure. Apply this. Then this EI cat X is also normal basis in L2 TD. F hunt F cat is the Fourier coefficients of function f. Let WP positive functions on ZD satisfy for all k belong to ZD. We have the following inequality. We defined smoothness space FDW given by this. Obviously, FDW is a helped space with inner product as this, and also have also normal basis eta k is defined as this. This is also given in the talk of Kuhn. We remark that FDW is compactly embedded into L infinity TD or CTD if and only if this implies. In this case, FDW is a reproduced kernel helped space with reproduced kernel as this. This condition is assured to guarantee the reduced kernel is a real value function. Often we use normalization of reproduced kernel such that kxx is equal 1. This is equivalent to the condition this show. For two small q and less than v, we have if we have this inequality, then FDW is compactly embedded into LQ. We consider approximation problem APPQ FDW to LQ. This is the embedding operator. Is easy to see W cap 2 cap belongs Z are eigenpairs of operator W APP2 star APP2. Let lambda t cap be the long-increasing rearrangement of sequence W cap 2 minus 2, and eta t cap be the eigenfunction with respect to eigenvalue lambda t cap of W. Then lambda t cap, eta t cap are eigenpairs of the operator W satisfy this. We have this inequality. Since eta t k is orthonormal basis in FDW, we get any f. We have this inequality, and this similar to possible inequality. In this talk, we consider Sobolev space FDW is H mix S2 TD, or dominated smoothness with this. This R is 2, where S belongs to this. Is well known the space HS2 TD is compared to LQ if and only if S is greater than of 1 this. We consider the embedding operators IQ. Now we introduce the previous results. Below in deterministic setting, linear methods are always optimal. We have the following results. APPQ is this. And for this condition, we have the following inequality. This is in deterministic setting. by the dual theorem between Kolmogorov and Gelfand windows, which are equivalent to minimum deterministic errors. And notice that linear methods are always optimal. We get from estimator Kolmogorov n windows and get for all to Q. We have this asymptoticus and this asymptoticus. Now we introduce the randomized case results. For S greater than 1/2, we have the following in this. First, this inequality is for Q or 2 small than Q small than infinity. In this case, Q is small than infinity. Sorry, small than infinity. And and in this paper, they give the good estimates as this estimate in this paper. We think the upper bound is also this quantity of the we also conjecture this way. Note that all the equivalent constants in above formulas depend on the dimension D. Finally, consider uniform approximation problems in Kurbov space with a periodic tensor product reproduce kernel helped space with smoothness there. And on the normalized error criteria, we use the normalized reproduce kernel. This in infinity setting, on the normalized error criteria is equivalent to the normalized reproduce kernel in absolute error criteria. The information complexity is defined to the minimum n of linear function for which this where Kuhn shows that in deterministic setting, the user tensor product uniform approximation problems suffers from the cause of dimensionality. That is, we have this inequality. Kuhn also showing for about the Kurbov space uniform approximation of Kurbov space, the Monte Carlo method can break the cause of dimensionality and prove that this problem is polynomial tractability. That is, we have this and this means that about uniform approximation problem is polynomial tractable in randomized case setting. Now we give a construction of linear Monte Carlo algorithms. We first use the following proposition, which follow from this paper, and is key common for Monte Carlo approximation of helped space functions, where linear information. This proposition originates from massing and has been extended further in CAD, also discussed in Helmich, in the talk in Helmich. The proposition is called the fundamental Monte Carlo method. Suppose SH mapped to G is a linear ranked M operator from helped space H into Banach space G, and let for Xj be an orthonormal system in H, such that the SF is this. We use randomized rank N method as follows, where the random function Li omega is defined by this, and Gi omega, the random function is defined as this. Here, the Xij are independent standard Gauss random variable. Then we have the following estimate. In the real value functions, this 2 square 2 can be reduced, can be low to 2. Here, Xj are independent standard real Gauss random variables. Note that eta dj is orthonormal basis in FDW, and for x with d we have the following inequality. Here we have decome f as three part. SNF is the Fourier partial summation operator of f. Here is there. Now we construct a randomized linear method with cardinality 2n. For the AN omega is defined as SNF. The first part is the Fourier summation operator plus some the Monte Carlo function, where the IN omega is the summation of Fourier partial summation operator Sn, and the Monte Carlo methods, while the fundamental Monte Carlo approximation methods for the operator Snm from above proposition. Similar algorithm was considered in BK. We obtain the following estimate on the expectation normal with independent standard Gauss random variable. As first for this, we have the estimator as this. Note that the CQ is independent of M and N. Next, we consider Q is equal to infinity. In this case, we assume that for all this term, the following Minkowski inequality hold. Where C is absolute constant, and Am is dependent of T and P, also and D. PT and P. Then we have this estimate. Note that for this space of trigonometric trigonometric subspace, we have the following inequality, where C is a constant independent of D and M. This means that if this space belongs subset is a subset of this space, then we have the following estimator. However, this estimator is not good. For hyperbolic cross trigonometric space, function space, Hg is this. We do not have similar dimension independent estimates. Do not have. We conjectured we have this, but we cannot prove it. Now we state the main results of this talk. Assume that this, we have the estimate of this group, where CQ is constant, dependent only on Q. Let Q is equal to infinity, and assume that this condition. Then we have the estimate, this estimate. Now we give the main results to the tensor product independent reproduced kernel helped space. This space including Sobolev space of dominating mixed smoothness. We consider the tensor product reproduced kernel helped space FTW with normalized reproduced kernel LQ TD. In this space, we assume that omega k is a tensor of WKJ, where WKJ is a non-decreasing positive sequence satisfy this condition. This is normalized. And this condition is means that the convergence rate of one dimension is greater than half. Then we have the following estimate, which are not sharp in sense of order of n. We have this estimate. We have this estimate. And this estimate. This estimate means that in the information complexity satisfy this and this. Satisfy this and this. It follows that in randomized case setting, uniform approximation problems of tensor product space are polynomial tractable, and LQ approximation problems of tensor product space are strongly polynomial tractable. We know that in deterministic case setting, uniform approximation problems of tensor product space suffers from curse of dimensionality. Our results compare with the results of coolness. Our results is not good as this. Is D is D minus 2. So our results is not good as this. However, we can check, we have this. Next, we consider approximation IQ for all Q. First, we consider Q is equal to infinity. We said A is this, and B is this. B is this. 那么choose a suitable M. We have following estimate. In this case, we have the estimate is this, and this estimate is for all n, and this estimate is for n is greater than this, here we use the result of Ksn and Cs. Next, we consider Q is less than infinity with S greater than half. We have for this, we have this estimate. We have this. Note that the order of in rank is this. Hence, we obtain that the algorithm AM omega are optimal in sense of order. Finally, we consider approximation elements of Monte Carlo algorithm AM omega for Sobolev space of dominating mixed smoothness with small smoothness. That is in this case. We only consider convergence reorder of M with suitable M. For S is equal to half, we obtain this estimate. For S is smaller than 1/2, we have this. We conject the optimal AM are also optimal in sense of order for this space. Also, I think I can prove the S small than 1/2. I can this is greater than this. However, for this I cannot prove it. Thank you for your attention.
Thank you for your nice talk. Are there any questions?
There was some normalization assumptions in the case of L-infinity approximation.
Yeah.
Which served the purpose that the initial error is 1 for all dimensional problems.
Yeah.
So how did this assumption change for the LQ approximation problem? Because there you need some other normalization assumption.
I don't know. Since the LQ normally no bound, I don't know. They have seems to no results on the no bound of LQ. For Q is smaller than infinity.
But did you check the initial error for the LQ approximation problem?
I don't know. For LQ indeterministic, I don't know. The same no result.
Any further questions? Okay, then maybe I have a question. You considered a Q approximation for Q larger than 2. Right?
Yeah.
What is if Q is less than 2? You any idea?
Less than 2, there no superiority in the randomized setting. The Monte Carlo method is not superior to deterministic method. For Q is smaller than 2. So in this case, is suffice to consider deterministic case.
Okay. Any other questions? No, then I propose to thank all the speakers of the morning session again.